In the last video, we defined a series to be the limit of partial sums of a given sequence. And so in this video, we're going to look at a specific type of series known as a geometric series. Okay, so we'll first look at what's known as a finite geometric sum, and we'll call that sum S sub n. And notice that the sequence being summed here, this a times r to the k, is what we called a geometric sequence in the section 9.1 and 9.2 worksheet. Okay, so now here we're letting the index k vary from 0 up to n minus 1. And so if I plug 0 in for k, I'm going to get a times r to the 0. Well, that's just a. And if I plug 1 in for k, I'll get a times r to the first. That's ar. Then plug 2 in for k, ar squared. Then ar cubed, so on and so forth until we get to a times r to the n minus first power. All right, so now the key property of a geometric sum is that I can move from term to term in the sum by just multiplying by this number r. And we call this number r the common ratio of the sum. And the reason why this word ratio is used is that another way to phrase this multiplication property by r is to say that the ratio of any two consecutive terms is equal to r, right? So ar divided by a, well, that's r. Ar squared divided by ar, well, that's also r, so on and so forth. All right, so now let's go ahead and derive a formula for S sub n. So here we have S sub n, and note that if I multiply S sub n by r, well, a gets multiplied by r to give me ar, then ar gets multiplied by r to give me ar squared, then ar squared gets multiplied by r to give me ar cubed, so on and so forth. Now the term preceding a times r to the n minus first power, that's going to be a times r to the n minus second power. And when it gets multiplied by r, that's going to give me an a times r to the n minus first. And then lastly, multiplying a times r to the n minus first by r, that'll give me a times r to the n. And these two sums are really, really similar. Notice that if I subtract the two sums, what do I get? Well, on the left, I'm going to get S sub n minus r times S sub n. And on the right, notice all this stuff in the middle is going to drop out. So I'm going to get a, and then ar minus itself, that's 0. Ar squared minus itself is 0. All the way up until we get to a times r to the n minus first minus itself, which is 0. And then lastly, I'm just going to get a minus a times r to the n. All right, so very nice there. Now, a little algebra, factor out S sub n on the left side and factor out a on the right side. And then lastly, divide both sides by 1 minus r. So we get that S sub n is equal to the quantity a times 1 minus r to the n, all divided by 1 minus r. All right, so this is a nice closed form expression for S sub n. Okay, so for example, if this sum has lots and lots of terms, say 50 terms, it'd be extremely cumbersome to add that up one term at a time, so using a formula like this will be very, very useful. All right, so now, next thing I want to look at, okay, recall from question 7 on the 9192 worksheet, okay, we saw that r to the n, which note it shows up in our expression for S sub n right here, this thing approaches 0 as we let n approach infinity if r is strictly between -1 and 1, or put another way, the absolute value of r is strictly less than 1. Okay, so that then implies that if I take the limit as we let n approach infinity of S sub n, well, what's going to happen there is this r to the n term will drop out, and then this expression will simplify to just a over 1 minus r, or in other words, the first term of the sum, which is just a, divided by 1 minus the common ratio. All right, so now what I want to do is summarize these two results, and then we'll look at two quick examples. All right, so first, right, again, for finite geometric sums, S sub n, we just derived this formula, right? This is S sub n is equal to a, the first term of the sum, times this quantity 1 minus r to the n, all divided by 1 minus r. Okay, so one thing to point out here, the total number of terms we're summing here is n. Okay, and notice n shows up as the exponent in this expression on the right. Okay, so as an example, let's say I want to sum 3 times 0.2 raised to the k power. We're going to let k vary from 0 up to 5. Okay, so here a is 3, and r, the common ratio, is 0.2. Okay, so 3 plus 3 times 0.2 plus 3 times 0.2 squared, so on and so forth, until we get to 3 times 0.2 to the 5th. Now here, there are 6 total terms, and so to apply this formula, well, I'm going to get a, which is 3, times the quantity 1 minus r to the n's. This would be 0.2 to the 6th power, again, because there's 6 terms, and then divide all that by 1 minus r, right? 1 minus 0.2. And we get 3.74976. Okay, now, again, with 6 terms, it wouldn't be the worst thing in the world to add these up just one term at a time by hand, or even with a calculator, right? But this formula here does make it, even then, quite a bit simpler, a little less cumbersome. All right, so now, taking the limit of S sub n, right? S sub n is this finite partial sum, okay? So taking its limit is going to give us what we're going to call a geometric series, right? So, right, S sub n just adds up the first n terms of this sequence, a times r to the k. So this geometric series is going to add up all the terms of this sequence, a times r to the k. So a plus ar squared, and here we're just going to continue to add. And what we noted on the last slide there, right, is that this limit is equal to this quantity a over 1 minus r, as long as the common ratio r is strictly less than 1 in absolute value. Okay, so this series will converge to this quantity provided the common ratio is strictly less than 1 in absolute value. Now, if the common ratio r is less than or equal to -1, or it's greater than or equal to +1, okay, then you can easily argue that this series will diverge, and I've illustrated that here with this picture on the number line. So for r strictly between -1 and 1, you see here in blue, convergent, and then less than or equal to -1, or greater than or equal to 1, right, the series will diverge. All right, so now, as just basically a rewrite of what you see up here in blue, okay, I'm going to write the following, okay, the sum of a convergent geometric series, so a plus ar squared, so on and so forth, is equal to a over 1 minus r, or I'll oftentimes say it's the first term of the sum divided by 1 minus the common ratio. Okay, and again, this will hold provided that common ratio is strictly less than 1 in absolute value. So as an example of that, let's look at the series where we're going to sum 3 times 0.2 to the k, where we're letting k go from 0 to infinity. So notice it's really the associated series from the example we saw up above, right? Here we just added up the first 6 terms. Now we're going to add up all the terms. So using a over 1 minus r, so the first term there, right, is 3, divided by 1 minus the common ratio, so 1 minus 0.2. This gives us a sum of 3.75. And notice, right, 3.75 is just slightly larger than the sum we got in this example up above, right? So what that's saying is that if you add up the first 6 terms, you're actually getting most of the sum, right? All the terms basically passed, so all the extra stuff we're going to get past 3 times 0.2 to the 6th and beyond, right? They're not going to contribute very much. And so it makes sense that this is larger than this first example, but it's just not that much larger because those tail end terms just don't contribute very much. All right, well, that's a good place to stop. In the next video, we're going to look at question 2 on the 9.3 worksheet, where we'll just look at a whole bunch of additional examples of geometric sums. Thanks so much.